Hey everybody, welcome to the code review for the cryptocurrency ATM. So to jump straight into it, let's start with the input module for the entire ATM, which is the keyboard. So you can see the keyboard module is instantiated here along with the ASCII decoder for turning scan codes into ASCII codes. And finally, the user input module, which is handling decoding those ASCII codes and sending the proper information to the ATM and finite state machine modules. In the user input module, you can see the inputs are simply the clock signal, of course, and the ASCII code from the decoder and the input style from the finite state machine. And what the user input does is it essentially just translates the different ASCII codes and sends the appropriate signals to the ATM module, which handles all of the logic and all of the functions of the ATM. And some cool parts are if there needs to be a 4-digit account number, the code will wait until the 4th digit is sent to send the code to the ATM module, and same goes for the PIN number and amounts, like currency amounts. Moving on to the actual ATM module, this is where most of the computation happens. Here is where the balances are stored, so all of the accounts have to be pre-initialized and all of their balances are pre-initialized. So I allocated $500 and 5 Bitcoin and 10 Ethereum to every account. And I feel like that's a generous amount, so we'll roll with that. And also, moving along here, the conversion database handles all of the different conversion values between the different currencies. And finally, to authenticate all the different users, we have this authenticator module here. And essentially what it does is it compares the account numbers and PIN numbers that are taken in from the user input module and checks them against this database and returns if it was successful or not, and even has a deauthorization function when the user logs out back to the splash screen of the ATM. Speaking of the splash screen, that is best depicted here in the FSM module. Now, the FSM module is pretty much just all of the different states for the ATM. So the idle state all the way down to the menu and all the different functions such as show balances, converting, withdrawals, transfers, and all of their sub-states. But the one cool thing I like about the state machine is we used one-hot encoding to light up some debug LEDs on the FPGA, and I thought that was pretty cool. I thought that was something that we learned in class that we could actually apply, which was nice. And also we learned a lot about using different parameters to try and coordinate between the different modules when we were splitting up the work for all of the different, the input, output, and logic for the entire ATM. Moving along, we have the 7-segment display modules. These are very robust. They have several different instructions and just text strings for instruction whenever the states change, and tells the user what to do, input your account number, input amount to withdraw, that type of thing. And this also has all of the code for scrolling the 7-segment display from right to left, so you can see longer instructions. And yeah, that is the general overview of the entire system. But moving into the actual implementation here, it actually does implement in some way. Unfortunately, there are several timing errors and setup time violations that just it causes a lot of logic errors, and unfortunately, when you flash it to the FPGA, it does not perform as expected, and that is mostly due to how the ATM module works. Just the amount of layers in between the input module here and the actual ATM module here, there's about 15 or 16 layers in between the input and the final output, and that just creates too many hold time, just too many delays. As you can see here, the delay is 11 nanoseconds, and the requirement has to be 10 nanoseconds due to the period of our clock being 10 nanoseconds. So with that in mind, I'd like to at least show some simulation of the ATM module and its functions working, which we have here in this simulation. Okay, so I'd like to at least walk you through the test bench and simulation that we wrote for the ATM module, because in the simulator it does work as expected. Unfortunately, in implementation, those timing errors really are what broke the entire system. So starting out here, I'll run you through the test bench. We set our account and PIN numbers and the current state. So this is the splash state, which is the account number where the user is asked to input their account number. So we're going to set our account number as the first account in the ATM, which is 0000, and the PIN number is also 0000. It's not very secure. However, so we input those two numbers in, and then we send this ready signal pulse here to advance to the next state. And as we advance to the next state here, we move on to the next state, which is the PIN input. And again, we pretend that the user is entering in their PIN number of 0000, and at the end of that, we send another ready signal pulse. And that brings us to the menu state. So in the menu state, what we want to do is we want to convert some currency. So the first thing we're going to try and do is convert 1 Bitcoin to dollars. So what we do is we move into the currency conversion state, and we set the amount of money we want to amount of Bitcoin we want to convert as 1 Bitcoin, and then we send our ready signal again. So here we go. We set our amount as 1. We set the currency type we want to convert as Bitcoin, which is encoded as 1, and we send our ready signal. And after that ready signal is ready, we wait a little bit until we confirm the second currency type, which is dollars. So we set the currency type to 0 here. And we can see after the ready signal gets passed, our Bitcoin balance goes from 5 to 4, and our dollar balance goes from $500 to $19,285. I'd say Bitcoin is very much worth it. But at any rate, the next thing we want to do is we want to withdraw $100. So we go to the withdraw state from, we're assuming these are coming from the FSM again. So we select our currency type. The currency type we want to withdraw is dollars. We want to withdraw $100. So we keep our currency, we switch our currency type back to 0, which is dollars, and we select our amount, $100, and then we send our ready signal when we're ready. And after that ready signal comes out, you can see 19,285 goes down to 19,185. You've successfully withdrawn $100. Now, after you've withdrawn that $100, you also want to transfer $100 to another account on the ATM. So this will show that the multiple accounts are also working. So we move to the transfer state. We set the account that we want to transfer to, which is the second account in the list, 0001. And then we set our ready signal. And that progresses us on to the state that asks us to input the amount of money we'd like to transfer. So we set our currency type that we want to transfer as USD. See that here? It's still dollars. And after we are ready, we send our ready signal. And you can see $100 leaves the account, the balance of the first account, 0000. And now, to make sure this works, we go back to the idle state, which will deauthorize the current user and allow a new user to sign in. So we set our new account number and our new PIN number, and we have the user go through the typical account and PIN number states. We make sure they have inputted both their account and PIN number properly, and then we show our balances. And as you can see here, $100 from the previous user's balance that we withdrew here, or we transferred over here. It's $100 over the base. The base is $500. That extra $100 is in the account of 0001. So, in theory, the ATM works, and I thought it was I tried to make as robust of a version as I could, trying to be as safe as possible and try to utilize the different parameters and states and all of the pre-planning to try and make everything as smooth as possible. But unfortunately, the reality is our implementation was too computationally intensive for our clock signal, and there's just too many layers for the clock signal to flow through, and that causes setup time errors. So, yeah, just to go over who did what. Chase and Marat worked heavily on the input module, and they did a good job. I worked primarily on the ATM and FSM logic, all of the parameters and the states, and tried to make it easy for the input and output guys to integrate their code into the overall system as best as possible. But again, the implementation just didn't want to play nice. And finally, Dohun did a great job with the display and making it scroll and all of that. And there's going to be a demo video for that and for the keyboard input as well.
So this is our initial state, which is saying welcome. And then if user hits enter, it goes to account number state. So user will be entering account number, then if the status comes out to be existing, then it moves on to the next step. So this state is for users to input PIN numbers to check validity according to the data we have. If PIN number matches designated PIN number according to the account number, then it moves to menu section. So basically there's 4 choices in menu section. First choice is show balance mode. So if user selects show balance, then it will show all the balances with different currency. If user choose withdraw option, then it goes to state for withdrawal, and also have option for convert currency. So that user can convert currency from specific one to another. Then lastly, you have transfer menu option, so that user can transfer money from one account to another account.
So here's a demonstration of our keyboard with 7 segments display. As you can see, when we press different numbers, it represents them on the keyboard. 1 to 0, 0 to 9, all of the numbers. Additionally, we also our decoder is able to detect the letters and turn them into representation of 7 segments. So A can be represented as A, B is B, C is C, D, E, and F. So through the data we get from PS2, we get our ASCII decoder, and we use it to represent letters additional to the numbers. So here's our PS2 receiver code. PS2 receives and outputs the keyboard data as a 32-bit key code out. And in our ASCII decoder, we turn this 32-bit scan code into 8-bit ASCII code in a hex format. So it's a smaller storage, and we only get the values that we need. And we only get the values for lowercase. We don't get any uppercase values. And after we get this hex code, we use them in the user input, which is Chase is going to talk about now.
Yep. In the user input module, we also process some specific characters, such as, let's see, the keys. Wait, where's the B and all those? Oh, up here. So to change the type of inputs to balance, to convert between the 5 different types of cryptocurrency, to withdraw, or to transfer between another account and another, you set the T key, the W key, the C key, or the B key. And then also we have the Q key enabled in an always block at the very beginning, such that any time that it detects a hex 71 and you press the digit Q, it gives a status code exit, which will exit the program and reset the state to idle. Also, we are concatenating the digits such that you can get a 16-bit representation of the PIN numbers and of the account numbers from multiple digits from the keyboard. And we use the curly brace operators to concatenate like that. And then finally, there is the ASCII to binary, which is converting from the hex codes, as Murat mentioned, to binary, and sort of a BCD style. But yeah, in any case, we import the states, and then the case for every received byte that is received properly is going to be converted for 0 through 9, because anything greater than 7, we need the 4th bit to represent it.